Okay, so, oh, I guess we're recording. So, um, this is stuff we did in the last lecture at the end of the course. So, welcome to the X lectures, the extra lectures that I never get around to giving during the 10-week course. We had one lecture on moving into second quantized operators, and I can't remember how far we got. I don't, and those of you who took this in previous years, I'm not sure how far we got into this stuff. So we just introduced the occupation number representation, creation and annihilation operators, which create or annihilate, and we're just going to be focusing on fermions. So everything I'll be talking about is fermions, not worrying about bosons. So they will, and this is my abbreviation I was using for the vacuum state, just abbreviating the vacuum state like that. So if I act on the vacuum state with this creation operator, AI dagger, I create one electron in state phi I, and that's sort of an abbreviated form, because my one electron really means, this is sort of the full form you would write this, one electron in state I, and zeros everywhere else. The fermion operators have the usual anti-commutation relationships. For AI dagger, the anti-commutator is delta ij, and all the other anti-commutators give you 0. And this, what I circled in the upper left is just really shorthand notation for a Slater determinant. And so when you these relationships down here are the equivalent of, say, switching two rows or two columns. And when you switch two rows or two columns, you introduce a negative sign in a determinant. So it's like AI AJ equals negative AJ AI, right? Or AI dagger AJ dagger is negative AJ dagger AI dagger. Okay, what else did we do? Field operators. So, if you look at the discussion of Federer and Waleka, they introduce everything using field operators. So the field operators, you can think of what we talk about over here as our usual, beloved localized orbitals. These single particle localized orbitals phi I, this would be representing one electron in our localized orbital phi I, for example. Some orthonormal basis, and everything I'll be talking about is an orthonormal basis. So this is our localized orbital basis, and then we could go to these field operators, and this would be simply your position basis where you create, so psi dagger R acting on the vacuum state creates one particle at position R. It's just the position representation as opposed to some localized orbital representation. And we know how, our position state, I can just insert the identity operator here, right? That's all I'm doing here. I insert the identity operator. And then, this thing here is just my wave function. And this thing here is my AI dagger acting on the ground state, on the vacuum state, on the vacuum state. And so this is how the field operators and the transformation between the field operators and the localized orbital operators so everything acting on R here, this phi I star, AI dagger acting on AI dagger, that's going to become your field operator. So the final answer is down here in the red box and in the two red boxes. So psi dagger is this sum over I, phi I star R, AI dagger. and similarly down in the lower left-hand corner. So we can just transform back and forth between the two. All right. And this is, this looks very much like what we did before as a wave function expansion. Now these, the psi's are field operators. If you just think of psi as a wave function, it looks just like what we would do for the expansion of a wave function in terms of the localized orbital basis. But in this case, these are the operators. The psi and the a are the operators. And in this representation, this phi is simply what you would call a C number. It's not an operator. So the operators are the AI dagger and the psi dagger here. And phi is what you would call a C number. So it doesn't have any, anti or commutation relationships. It just acts, in this representation, it's just acting like a number. And since, psi dagger acting on the vacuum creates an electron at R, the electron density operator is simply psi dagger psi at R. So if that acts on any state, it'll be it'll just give you 1 if there's an electron at position R, or 0 otherwise. Just give you 1 and 0. Can't remember what yeah, we'll leave it at that. There may be some units, some volume units, some d cubed R involved, but I'm not going to worry about that. And so if I want the electron density, I just need the expectation value of psi dagger psi. That's going to give me the electron density at position R. And then, putting in the relationships we just derived between psi and the localized orbital a dagger a, just replacing the psi dagger psi with its, in terms of a dagger a, the expression right below in blue is the same expression in the localized orbital representation. Just substituting in what we had just derived, relationship between the psi's and the a's. And for those of you who are sitting in the course, we talked about this, that we had derived an expression for n of r in terms of this, our G superscript n here, and said that this was simply the density matrix, rho Ji. And so this thing in brackets is indeed the density matrix, rho Ji. This a dagger A. And this is exactly how you, take the expectation value of something. You multiply something by the density matrix and you trace over everything, right? So the sum over ij is a trace. All right, so we had already derived this in the previous chapter, I think, on non-orthogonal basis. And so this was just to show that we're coming back to something that we had already derived. If I want the total electron density, I just integrate my, the electron density over everything, integral d cubed Rn, which over here on the right is, just affects that phi I star phi j, which just gives me a delta ij, which collapses the sum. So I just get that n is the sum over all I of ai dagger ai, the expectation value, which is the sum over all I of rho ii, right, which is the trace of rho, which is the usual relationship between the total number of electrons and the density matrix. Okay, so we have these operators. So in this occupation number representation, the operators are your creation and annihilation operators. Everything else is a C number. And so now we need to be able to write the Hamiltonian in this representation in terms of creation and annihilation operators. All right. So here's our usual Hamiltonian, H0, and the way we transform this into the second quantized representation is given by the line below here. So this is how you transform any single particle Hamiltonian, where these are your field operators. And so if you go ahead and expand out your field operators in terms of the AIs and AJs, you get the next line down there, and you see the integral is just giving your usual Hamiltonian matrix elements that we've been working with forever in the localized orbital representation. And yeah, so this is what you end up with. Our Hamiltonian operator in the second quantized representation is simply this, or Hij, or your usual matrix elements that we've been working with since 208, and the AI dagger Aj are your operators. And often, this is, if you can write it like this, it's just quadratic in the operators, and it's a single particle Hamiltonian. And a single particle Hamiltonian can always be solved exactly. And if you can solve it exactly, that means you know the eigenstates, you can diagonalize it, right? And if you know the eigenstates, in the eigenstate basis, it's just going to look like this, where I would just be whatever your eigenstate is. And often, in the physics textbooks, the eigenstate is going to be of just your single particle Hamiltonian is going to be some plane wave or block state that you can write like this, some plane wave eigenstate. In EK would be your eigenenergies. Okay, and in our scattering state basis, which underlies everything we do in Negev, we could write that like this in the bottom line, where you simply break this up into two sets of states with the indices k sub L and k sub R. And so with the index k sub L means you're injecting from the left contact, and the index k sub R means you're injecting from the right contact. So this is what this would look like in the scattering state basis, right? Because the scattering states are eigenstates of the single particle Hamiltonian, and this would be what the Hamiltonian looks like in your scattering state basis. Now, there's also this other part, the electron-electron interaction part, and this is the way that is second quantized. You need, because it's a function of both r and r prime, you need to do a double integral, so there'll be two psi daggers, two psis. Order is now important, and so this is the way the operators are always ordered, right? In terms of, and when we expand them out, the order of the, so if we expand out this expression back into our localized orbital representation on the next line, then it looks like what's written on the next line. And now you can clearly see why the order has to be maintained. And the C daggers, have to appear before the C's. And since, V of r minus r prime is really a C number in this representation, we could put all the psis on one side or the other of the V, but the order of the psis has to be preserved, just like the order of the C's has to be preserved. And so the that Vijkl is that integral just written down below. Okay. We aren't going to do anything with this for a while, but this is your very generic second quantized form of the electron-electron interaction. And I think, I didn't go any further with that. In the notes, which I have now, I reduce that. I use the usual plane wave basis, and I reduce that to the form that you see in the standard textbooks. I may still have that up here. Let's see. It's just in the notes, just to show you that we get the usual expression. So we just looked at it in this, in some arbitrary basis, and had this Vij Lm. And now if we use our our plane wave, our usual plane wave basis, then this just becomes in this form that you often see it written in textbooks. Or if we just work it down, we can first write this as its Fourier transform, take the matrix elements. And the matrix elements are now just going to be matrix elements of a bunch of plane waves, right? Here's the R dependence of this and all the other plane waves from all the other phi's. And so you just get a Kronecker delta, and you work around, you switch some indices, and finally you get it into the form, which I even give you the exact equation in Mayhem. All right, so this is the usual type expression that you see in the second quantized representation. So that's in the notes, and they'll be uploaded. All right. So that's just to show that there's nothing unusual. This is a standard thing that you see in the textbooks. All right, what next? And then we talked about the three representations, Schrodinger, Heisenberg, and interaction. So Schrodinger is the one you're used to working with. And this is the equation of motion. And you can formally write down the solution like that. And this is just your standard, what you start with, right? Like first semester quantum mechanics. The Heisenberg representation, the wave function transforms like this. So psi s would be your Schrodinger wave function. Psi h is your Heisenberg wave function. And if you go ahead and take the derivative, you'll see that you just get this down here. So in the Heisenberg representation, the wave function has no time dependence. Okay. Just blindly taking the time derivative of the line above that, that's what you get. You get 0. So there's no time dependence in the Heisenberg wave function. And then we looked at the transformation of the operator. So to go from a Schrodinger operator to a Heisenberg operator, this is a transformation, and the way you do that is you look at matrix elements. So a matrix element, the value of the matrix element has to be the same independent of the representation. So we write down an arbitrary matrix element in the Schrodinger representation, and then this is the relationship between our Schrodinger and Heisenberg wave function, and you just put that in, and you end up with this for your matrix element in the Heisenberg representation. So the thing in the red box is the transformation of an arbitrary transformation for an operator from Schrodinger to Heisenberg. And then we can look at the time dependence of the operator. So in the Schrodinger representation, our operator has no time dependence. In the Heisenberg representation, it does, and it's just given by the anti-commutator, right? So in the Heisenberg representation, our operator evolves in time according to the anti-commutator. That's the time derivative is given by not the commutator. The commutator, OH comma H. And the final one, so you've probably run across these. The final one is probably the one you've had the least experience with, is the interaction representation. And again, we need a bare Hamiltonian that you can solve exactly, and H prime. So this is what you use when you do perturbation theory. Okay. And so the transformation between, again, the Schrodinger wave function and the interaction wave function is given by that. And so then you can just go ahead and take the time derivative of your interaction wave function, just work through it, and you get finally what's written down on the red line down below. And so the two terms in the underbraces are, so the final expression is this, IH bar ddt of psi sub I, that's in the interaction representation, It's just given by h I prime, so that's h prime in the interaction representation times psi I. And so h prime in the interaction representation is this thing here. That's h prime in the interaction representation. So that also gives you the transformation of any arbitrary operator from Schrodinger to interaction. That is the transformation of the operators. And now an important point, which I didn't mention last time, is that even if h prime in the Schrodinger is time dependent, so even if this is h prime of t in the Schrodinger representation, everything I've done still holds. And so the equation down at the bottom is still correct. Nothing changes, even if h prime of t is a function of time. H prime of t in the Schrodinger representation. Even if h prime is a function, even if this guy is a function of t, everything I've done still holds. And we're going to need that when we start doing adiabatic perturbation theory, because we're going to slowly turn on h prime with this exponential turn-on factor in e to the negative eta t. So adiabatically turn it on. In the interaction, so this is the transformation of any operator from Schrodinger to interaction, and then you just take ddt of that, and you get that this time derivative of any operator in the interaction representation is just given by its commutator with the bare Hamiltonian. So the bare Hamiltonian determines how it evolves in time. And I guess here you would have to make, I guess you, if OS is a function of t, then you'd probably have, I guess you'd have to add one more term. We had h prime as a function of t. If this thing to start with is a function of time, then you would end up with one more term, plus IH bar ddt. Is that right? I guess you'd still have to keep your e to the IH0, and you would have to add on to it in this central region plus this IH bar ddt OS t. I think that's right. Because the e to the IH0t, e to the plus or minus IH0t does not commute with OS. So they'd still be hanging out there. At any rate, I don't think that comes into play. It's just something to throw out there. The thing that is important is the fact that this still holds true, even if our interaction is time dependent. Green functions. So in this second quantized representation, how are they defined? And this is how they are defined. This factor of 1 over h bar out front, in so many physics tests, h bar equals 1, so you never are quite sure where it should be. I defined it this way, so the equations of motion will give me just a delta t minus t prime on the right-hand side, as opposed to like an h bar delta t minus t prime. So And when I want to integrate, say, the density of states, I integrate integral dE over 2 pi instead of integral dE over 2 pi h bar. So at any rate, this is the way I've defined them. And this is the way I've worked with it for, since a grad student. So these are my green functions. And we'll just see what equations of motion. It all works out. Most physicists wouldn't even be concerned with h bar. Just put it in at the end. Anyway, so our g sub n, right, this correlation function, this is not really a green function. It's a correlation function. This is what we, finally need to calculate to get like electron density or current. That's how it's defined in this second quantized. And the brackets indicate an equilibrium, just a thermal average, like a grand canonical ensemble average, or a non-equilibrium. It's a non-equilibrium average that we have to actually evaluate using negative. It's the way we evaluate it. So it's a statistical average. And the other green function that we during the course never really used was this one, which is just the same as g superscript n with an I out front. So it's just a factor of I is the only difference, the g less than. But in the negative literature, when we start working with time contours and all that stuff, getting into the hardcore stuff, it turns out that it's easier to manipulate between all the different green functions, just keeping this I around, because all the other green functions have an I in front of them, and so you don't have to put in I's and stuff. So this one is more intuitive in terms of its physical interpretation. This one just comes out naturally from manipulating the green functions on the Keldysh contour. What's this next one? Oh, what we call G sub p. Again, so this would give you the whole density, right, or the whole current. We've just flipped the order of the A and the A dagger from G superscript n to G superscript p. Later, the p confused me for a moment because later we're going to have a path-ordered green function, but we're not there yet. So these are the ones that we've been dealing with and throughout the course, G sub n, G sub p, to give you electron density and hole density. And just like G sub n had this sort of G less than, well, G sub p in a lot of the green function literature, they'll use G greater than instead, and the only difference is a factor of negative I in this case. And the negative I, when you switch the order of your operators, you introduce a negative sign. And you can think of that's where that negative sign is coming from, a difference in sign out in front. The retarded green function, which is probably what we spent the most time worrying about throughout the course, is defined like this. In this second quantized representation, you've got your unit step function out front. So it only exists for t greater than t prime, some factor of minus I over h bar, which we can ignore. The important stuff is what's in the brackets. And you can see that what's in the brackets is an anti-commutator. The thing in the brackets is an anti-commutator. And if we look back at the definitions of what we had for this G superscript n and G superscript p, it's trivial to see that GR is related to this GN and GP like this. So it also equals that. And this is, when you use GN and GP, you got to throw in these extra factors of I and negative I to make the equivalence. And that's why G greater than and G less than are perhaps more natural when you start writing down all these relationships between the green functions. So just using the definitions we previously had, this is true. The advanced green function, well, we just flip the order of t and t prime in the unit step function, because one only exists with t greater than t prime, the other one only exists with t prime greater than t. Well, the sign of the I changes from minus I to plus I, and the stuff in the brackets stays the same. All the stuff in the brackets remains the same. Because if you look at the stuff in the brackets, it's if I take the dagger of that, it's the same thing, right? If I take the dagger of all that stuff in the brackets, nothing changes. Because one term just goes into the other term, right? And so the thing in the brackets is remission. And so we said that GR equals G, a dagger, when we were working in the energy, in terms of energy, which we'll get to in a moment. So if you think of T and T prime as just like matrix coordinates, we flip T and T prime, and we introduce a negative sign. And so we still have that same relationship between GR and GA. Our spectral function, another thing we spent a lot of time working with, is given on the next line. And again, the thing in the brackets is exactly what we had in the brackets for GR and GA. So the thing in the brackets hasn't changed. It's the same anti-commutator between AI and AJ dagger. And these are just some relationships that hold true that we've already derived previously in that sort of single quantized representation that we've been working with all quarter, and now you can still see that these relationships still hold true in the time domain and in the second quantized representation. We derive this like A is I, GR minus GA in the energy domain with the green functions we were working with previously. You can see these definitions preserve all those relationships that we had before. Everything we do is in steady state, and so this is how, in steady state, the assumption is that all these things are only a function of the time difference coordinate. So the center of mass coordinate, nothing is changing with time. They're only a function of the time difference coordinate. And so this is a Fourier transform that you use to go from the time domain to the energy domain, which is what we've been working with all quarter. And I guess to go back the other way, I don't know why I didn't write that down. So to go the other way, I guess I would have Gn of T minus T prime is equal to integral dE over 2 pi h bar, I believe, e to the minus I e T minus T prime over h bar. Right, that would be going the other way from energy to time. And so if you look at this expression here, it just when t equals t prime, that's just the integral of overall energy in the energy domain, right? This is sort of like something all the EEs know from signal theory, right? When you're doing this in like an autocorrelation function, right? At t equals t prime, it's like the integral over all frequency, right? And so this is same thing here. If I remember, I had that 1 over h bar in the definition of all my time functions. So if I multiply through by h bar, get rid of that here, then the equal time correlation function is exactly just the integral divided by 2 pi of its energy representation, right? And so this comes back to something that was done in homework 1. Here's our spectral function, right? There's our definition of our spectral function. And in homework 1, you were asked to show that the integral, you were asked to show this for a rather specific case, that the integral of the spectral function was equal to 1. We had a specific form for the spectral function. And there was a comment that later we would show that this is just a result of the anti-commutation relationship. So if we look at this, if we look at our spectral, if we, using this relationship up here that we were just talking about, setting the integral of, my spectral function over all energy is just the equal time, is just evaluating my spectral function at t equals t prime, right? And at t equals t prime, well, we said this is an anti-commutator. So my equal time anti-commutation relationship is that my spectral function is just 1 over h bar Kronecker delta ij, right? T equals t prime. 1 over h bar Kronecker delta ij. Independent of anything. It's a completely general statement. Looking at this definition here, right? You said t equal to t prime. And that just gives you the equal time anti-commutation relationship. And so the thing in the brackets is delta ij. So at equal time, the spectral function is just, and we said at equal time, that's the integral over all energy divided by 2 pi, right? And so, I guess I show it over here somewhere. I don't know. I mean, if you said t equal to t prime, I don't know how I did this. Okay, at any rate, so the equal time, this thing at equal time multiplied by h bar is just going to be 1 when I equals j. Right? A at t equal t prime times h bar. It's just 1 when I equals j, which is what you had to show in homework number 1 at the beginning of the course. So this is a very complete. This shows that this is all this is a statement that there is one. We said the spectral function is like density of states. So this is saying that there's one. I want to say one state. One state at. One state per state. I don't know quite how to say it. There's a total number of states in state I is 1, right? That's all it's saying. All right. What else? Okay, one that we haven't seen before. We will need this is a time-ordered green function, and it's defined like this. And it's really when we do perturbation theory, it's really the green function that underlies all the others, and from this one come all the others. And this is the one that we actually work with when we do perturbation theory. And this t here is a time ordering operator. And the way to remember what it does is that later times occur on the left, so that time progresses. Earlier times are on the right, later times are on the left. Time progresses from right to left. So maybe I don't know. Does anyone have a language that goes like that, right? Because, English goes from left to right. But here time progresses from right to left.
Arabic.
What's that?
Arabic.
Arabic? Is that the way they Okay. Okay. Well, I guess we don't have any. All right. Anyway, so time progresses from right to left, and this is what the time ordering operator does. So if t prime is greater than t, then these two operators get flipped, and a negative sign is introduced. So we can explicitly, what that means is written down here below. So this is what this means explicitly using the unit step functions. When t is greater than t prime, we have this minus I over h bar ci cj dagger, and when t prime is greater than t, it's plus I over h bar cj dagger ci. That's explicitly what this thing is. And then there's, this is related to other green functions like this, which come in, we need to make use of later on. So all these green functions are interrelated. And you just go back, and using these definitions that we just wrote down, it's trivial to see that these relations are indeed true. Okay, so now the thing to do is show that using these brand new definitions, we get back the same equations of motion that we've been working with all along. So, we had this equation, and we haven't, we're not going to worry about self-energies yet or breaking up our domain into device and leads and all that. We're just going to see if we get back this equation of motion for the green function and this equation of motion for g less than, and this is what you get if there are no sigmas around to worry about. And so the first thing, it's easier to start by evaluating this explicitly using the definition over here. So the ddt only operates on t, not t prime, all right? And so we get this line down here where I underscored in green where the ddt is operating. So the cj dagger t prime just goes along for the ride here. Nothing's happening to it. It just goes along for the ride. So we just need to evaluate ddt ci of t. And I guess I forgot to mention that all these definitions, the operators are in the Heisenberg representation. That's kind of an important point. Sorry. So for all these definitions, all the operators, all the creation and annihilation operators are in the Heisenberg representation. And so in the Heisenberg representation, we know how to evaluate that time derivative. We just have to take the commutator with h. That's how we evaluate the time derivative. So we go ahead and do that. And I'm just going to look at the single particle h here, which generically has this form right here. So this is a completely generic form for any single particle Hamiltonian. And I'm going to use that to evaluate my commutator. And so, those of you who've done that, there's some simple expressions that you can immediately write this down, but I thought, let's just work this through. So the way you do that is you take one term or the other and you push through the CI all the way. So we're going to take the term and underscored in red, and we're going to use our anti-commutation relationships to push that CI through to the other side to make it look like the second term, and hopefully something cancels and this simplifies. So that's what you proceed to do. And so we go ahead and do it here. So the first thing, when I look at CI-CM dagger, using the anti-commutation relationship, that's just equal to delta IM minus CM dagger CI. So CI CM dagger plus CM dagger CI is delta IM. So I'm going to replace the CI CM dagger with this delta IM minus CM dagger CI. And so I do that. So I get two terms, right? I get delta IM times Cn minus this other term over here on the right. And now I push the CI through the Cn, and those two things they're CI/CN plus CN/CI 0. So by pushing it through, I just pick up a negative sign. And so this negative sign and this negative sign give me a positive sign. And so finally this term, what's left, this term here cancels this term here, and I'm only left with that term in green, the delta IM/CN. So I put that back into the sum, and that kills off, one of the summations. And so finally I'm left with this down here. And so I put that, so now I have this expression for my IH bar ddt of G less than. And that equals that. Right? When I do that anti-commutator, that's what I get. And so in matrix notation, that's just a matrix multiplication of H times G less than. So I get my equation of motion that in the time domain of this, which in the energy domain by Fourier transform to energy is this, which is what we wanted to show. And if you look at the the definition for GR, I've got the, and now I'm going to take the time derivative of our retardigreen function. It's only going to act on this term and this term, which we've already worked out. Right? We've already worked out exactly what happens. And so when IH bar ddt acts on those terms, I get exactly this. I get back H times those terms. So the IH bar ddt acting on that thing in brackets is just going to give me H multiplying that thing in brackets. If you think of it as matrix multiplication, H times that thing in brackets, which is just H times, the IH bar ddt acting on the stuff in brackets is just going to give me back H GR, just like it gave me back HG less than. It's going to give me back HGR. But I have a new term here. I got to take into account that the IH bar ddt acting on the theta term. Right, that's the only novelty here. The IH bar ddt acting on this stuff in the brackets just gives me back HGR, just like it gave me back an HG less than. But I have one more term due to this. Okay. And so that term, is so IH bar ddt acting on this, right? The IH bar is canceled by this. IH bar times negative I over H bar gives me 1. And I get ddt of theta, so that gives me delta ij. Delta t minus t prime. Right? So I just get ddt acting on theta t minus t prime gives me delta t minus t prime. And so the only time I'm going to get anything non-zero is when t equals t prime. So for this term, I set t, in the rest of the expression, I set t equal to t prime. I can set t equal to t prime since that's the only time I'm going to get anything. And when I set t equal to t prime, I get delta ij. Right? So from that other term, I just get delta t minus t prime delta ij, which is written on the top line up here. So this is from IH bar ddt acting on the step function. I get that term. And from it acting on the other stuff, I get this term. And so you put all that together, and you going into the energy domain, this just becomes your identity on the right-hand side. This is just like what we had for our G less than. It's just because I had that unit step function that I get, this inhomogeneous term on the right-hand side, which is the identity. So again, we get back our usual equation of motion for the retarded Green function. It looks like an impulse response. Okay, so all our equation of motion still hold using our new definitions. I'm going to skip this because I'm going to do it better. We talked about, manipulated the equations for a while, but I just needed to make sure you understood the basic definitions before we moved on. Time dependence of our Schrodinger wave function at any time. So this is just whatever it was at time t equals 0, t0, and this is whatever, this is how it evolves with time, both t greater than or less than t0. Right? This is the time dependence of the Schrodinger wave function. This is the transformation between Schrodinger and interaction representation. Right? This is our generic transformation, how we go from Schrodinger to interaction. And so psi s of t, well, we just put this thing here back in for our psi s of t. Right? This is psi s of t. This is our transformation interaction. And now to go from psi s to psi I multiply and divide in here by e to the minus IHT0 times e to the plus IHT0. So e to the plus IHT0 times psi s gives me psi I. You see that? And this one just stays around. And so this is how psi I evolves with time. Just starting from what we know with the Schrodinger and how psi I transforms from psi s, the transformation between psi I and psi s. So down here, I just stick in an e to the minus IHT over h bar times an e to the plus IHT IH0 T0 over h bar. And let's see, did I get that right? Yeah, that's right. Notice that this is T0. This is important. I made this mistake at first. This is T0, T0, T, and T. All right? It's kind of important. And it looks like did I get it right? Yeah, I got it right. So this thing here underscores something that's crucially important for this whole discussion of adiabatic perturbation theory, this propagator, u of t comma t0. It's also referred to as the S matrix. It defines how your wave function in the interaction representation evolves with time. And if you just look at its definition here, you can see that it's unitary. If I dagger it, what happens? Let's see. If I dagger it, so u dagger is the inverse of u, right? Because I flip everything, and then you just multiply everything together, and you'll see that it cancels. Because if I dagger it, this will get moved over to this side, and I multiply, and all the signs and the exponents are going to cancel each other. So u dagger tt0 equal times u tt0 gives you 1. So it's unitary. U dagger is the inverse of u. And again, if you just look at what's going on up here, it's trivial to see that it satisfies this group property that u t1 t2 times u t2 t3 is u t1 t3. So you can just string these together, right? You just string them if you want to evolve, like from T1 to T2, T2 to T3, et cetera, et cetera. And also, by flipping the T and T0, I mean, either from looking at the group property or looking at what it means to dagger it, it's probably easiest from the group property. UT0T times UTT0 is just going to give you UT0T0, which must be the identity because you haven't propagated it anywhere. So if I flip the T and T0, that's also the inverse, which is also the dagger. Yeah, again, from the group property. This is just going to give me U of TT, which, since you aren't propagating anywhere, it's going to be the identity. Okay, so that's all good. But this is not a very useful expression to work with in practice, this definition up here. So what we want to do is develop an iterative expansion for U that, you know, if we can develop something that looks like a power series expansion, then we can, you know, start using perturbation theory. And so that's done like this. So we know this is how, you know, our wave function in the interaction representation evolves with time. That it just evolves according to this S matrix, UTT0. Right? That's the time dependence of the wave function in the interaction representation. We also know that this is true. This is the equation of motion for the wave function in the interaction representation. And this is true even if H prime in the Schrodinger representation was time dependent. And this is what we just talked about a little bit ago. So this is the equation of motion for the wave function in the interaction representation, and I indicates that, you know, this is H prime in the interaction representation. Okay, and so now we just replace psi I of t with this. Okay, we replace psi I with this up here, and so, you know, now we just have, and so do that on both sides. This psi I t0 is just a constant on both sides, and so you end up with this equation of motion for your propagator or your S matrix. Just on both sides of the equation, replace psi I with this thing. So the only time dependence is in right here, U t comma t0. And so that gives you an equation of motion for U of t0. And we can integrate this. It's just a first order linear differential equation. So we go ahead and integrate it and evaluate it between t0 and t. Okay? So on the left-hand side, I get this. On the right-hand side, I get this. Right? Just integrating that first order differential equation. And so, moving this over to the other side, this is what we finally get for the integral solution to that first order differential equation for U. And U occurs on both sides of that equation, and so you can immediately think of starting to iterate that equation just like you would iterate a power series. And so that's what I do on the next line. I show the first iteration of that. If you were to just start iterating that, like you would iterate a power series. So this would be, and the first time you just put the 1 back in here and get this term, right? And next term we went through this before. I always get confused. I have to do this in the dark corner, but this is Adiba had to straighten me out last time. So at any rate, this is how you can, I think you can all see that you could go about iterating the solution to that equation, right? And create some infinite, something that looks like a power series, but it's not quite a power series yet because, you know, this this variable of integration shows up in the limit. Like for each integral, the upper limit of the integral is, you know, the variable of integration for the preceding integral. So they're all kind of interconnected, which kind of still makes it, we would like it to be a power series, and it's really not quite there yet. Okay. And so the way you handle that is a little bit tricky, but it's just a matter of changing the order of integration and playing with this a bit. So if we look at this, like, let's look at this expression. We have a double integral over t and t prime, okay? And so you can think of a plane of t prime and t double prime, and we're doing this double integral. And you want to look at, you know, what part of the plane you're integrating this on, which I'll show you in a second. So this is a region we're integrating that in this t prime plane. So this is t prime, which is the outer integral. T double prime is the inner integral. And so the lower limit for both is t0. Let's see if I can write on this. So we integrate the inner one, t double prime, from t0 to t prime. So I'm integrating t double prime from t0 to t prime, right? And this diagonal line is when t prime equals t double prime. And then I'm integrating t prime at each time I integrate t prime up to t here. All right. So this is what we're doing, and this is the way the integral is set up. And what we do is we change the order of the integrals. So it's like first you do t double prime, and then you do t prime. And if we reverse the order of the integral, then we get something that looks like this. And these are all dummy indices, so we can just switch what we call t prime and t double prime. And then if we look at what we have here and look at what we have here, let's see, is this what I want? Integrating from t prime to t. Yeah, this is what I want. So if I look at these two terms, right, the outer term is the same. The outer integral is the same. But look at the integral, the inner integral. This goes from t0 to t prime. This one goes from t prime to t. If I add those two integrals together, I have something that goes from t0 to t. Right? If I add this one to this one, this goes from t0 to t prime. This goes from t prime to t. I just get an integral that goes from t0 to t, which is what I'm trying to achieve. And since they're equivalent, I just add them together and divide by 2. Right? I add them together and divide by 2, and now I have both integrals go from t0 to t, which is what I was trying to achieve. So that the inner integral, the limits of the integral don't depend on, is not the integration variable of the outer integral. Right? So they all go from t0 to t. So if we do that, then I'm just adding them together, dividing by 2. I get something that looks like this. I had to reverse the order, and order is important. So, hi prime at t prime and t double prime may not commute. So you can't just, flip the order. So if we write it all out, we get this. The limits of integration are now the same, but I have these, depending on which is greater, t prime or t double prime, I got to carefully keep track of my limits. And the way to do that is with this time ordering operator that we just talked about with our time ordered green function. This is the same time ordering operator, later times to the left. And so now I can make it look very compact. All the limits of integration are the same, and I've got something that I was looking for that's going to look like a power series expansion. If we do that for all the terms, I'm not going to do that. This is what you get. So it's this infinite sum. It looks just like a power series expansion, where you are integrating this time-ordered product of our h primes of t. So this is the Taylor series expansion we were looking for. And of course, this is just a Taylor series expansion of an exponential. So formally, we can write this down like this, which is a shorthand way to write it down. And you can move the time ordering operator out front, and the way you interpret, that exponentiated integral is 817. That's what we mean by that, but that's sort of a shorthand way of writing it down. And so this is the S matrix that we need to do our adiabatic perturbation. Okay, so on to adiabatic perturbation theory. So this is sort of the fundamental starting point of your adiabatic perturbation theory. You have your single particle Hamiltonian that really know how to solve in some way or another, the trivial part, and you have some interaction term that you really don't know how to solve exactly, and you're going to have to treat using perturbation theory. And this is the adiabatic part, stuck in by hand out front, where you adiabatically turn this on. Eventually, we let eta, take the limit of eta go to 0, and so at t equals negative infinity, notice this is the absolute magnitude, absolute value of t. At t equals negative infinity, your Hamiltonian is just h0. At t equals positive infinity, it's just h0 also. At t equals 0, h is your exact Hamiltonian. Right? At t equals 0, h is your exact Hamiltonian. So both at plus and minus infinity, your Hamiltonian is just your bare Hamiltonian, h0. At t equals 0, it's your exact interacting Hamiltonian. And so as t goes to minus infinity, the wave function in the Schrodinger representation must just approach the solution of our non-interacting Hamiltonian. So our Schrodinger wave function just becomes this, where phi 0 is just the eigenstate of your non-interacting Hamiltonian. And we're going to start thinking of these as many particle wave functions, where in general and we're going to start off doing zero temperature perturbation theory. So this would be, say, your ground state wave function, phi 0. In general, we're going to be, when you do zero temperature perturbation theory, you really aren't doing an ensemble average. You just taking a matrix element of the ground state wave function, because at t equals 0, your system's in the ground state. There are no excited states at t equals 0. So this is your just throwing, you don't have to think about that, but this, at the moment, in terms of what we're doing formally, this is just your Schrodinger wave function. This is the eigenstate, and this is the time dependence of your Schrodinger wave functions in the Schrodinger picture, right? And your interaction wave function is also follows the same transformation that it always does between Schrodinger and interaction. This is a transformation as we take the limit as t goes to negative infinity. Then h0, this is just a number. h0 and phi 0 gives me plus. It can't. The phases, these two terms cancel. So the interaction wave function as t goes to negative infinity just becomes your eigenstate, your time-independent eigenstate at t equals negative infinity. Okay, so your interaction, your wave function and the interaction wave representation just becomes your time-independent eigenstate as t goes to negative infinity. And so then you let t increase, and the wave function in the interaction representation evolves in time with the adiabatic turn-on of your h prime term. Time is it? 4 o'clock. All right, let's just go a little further, and then I guess I have to go put my robes on. Actually, I still need to eat lunch. Okay, so that's all good. So, and then, you know, as this thing evolves, at t equals 0, then your interaction wave function is the exact wave function of the full interacting system in all representations. Since at t equals 0, all representations are identical. All those transformations were like an e to the I ht or h0t, but if t is 0, there's no transformation. It's just 1, right? So at t equals 0, all the representations are equal. So at t equals 0, your wave function and interaction, Heisenberg, Schrodinger, they're all the same, and they're just given by this. Sorry, there's an extra parentheses there. This parentheses should, half a parentheses. That shouldn't be there. Okay? So at t equals 0, this is your wave function. And it is exact if you could evaluate that S matrix exactly. Okay, so that expression is exact. Problem is you can't actually evaluate that expression. And so this U is given by this. So the only difference between what we wrote down previously and now is that we have this extra term in here because of the way we defined our H prime with this adiabatic turn-on factor. And as I said, eventually we let this eta go to 0.